Hey, hi everyone. Good afternoon. I am so excited to kind of introduce you to our next set of speakers. But before I do that, I just want to thank everybody, especially our teams, for kind of attending all these sessions and all the work that you're doing to create your programs. And as we go through this, there's a couple of different housekeeping things. One is the Q&A. Is where you would place any of your questions. In the Q&A, you would be able to upvote or downvote some of the other questions. There is a chat, and that chat, I think you can send also questions to the panelists, and I'll be monitoring that. And then, any other additional information, Meg has put in the comments, the website for the Big Ten Augmented Intelligence Bowl. We are planning to have a second one that will kick off in the fall of 2022. And so with that, I'd like to introduce our two guests today from Anthem. So Mark Shapiro is Senior Director at Anthem Exponential Technologies Center of Excellence. He leads the effort to develop AI and machine learning capabilities for digital healthcare. And then we also have Sasha Gutfraind, and he's Principal Data Scientist, also with Anthem's Exponential Technologies. Sasha and myself and Abel kind of go way back, so it's a small world in data science. And so with that, I'm going to turn it back over to Mark to talk about one of my favorite topics, which is about generating synthetic data.
Thank you, Ngan, and thanks for inviting us to give this presentation. So the topic of the first part is generating synthetic claims data. So the team that was involved in this project, it was Guido Moscioni, a senior AI engineer in our team, Abel Augustin, also machine learning specialist, Nishant Lakakula, and Bianca Marzellino. So the first question is, why generate synthetic data? One obvious reason is that, well, we can use synthetic data to validate or train machine learning models without the risk of violating privacy or violating legal requirements. Another, maybe even more ambitious reason is if we can peek inside the model that generates synthetic data, we may be able to understand what patterns and interdependencies it identified in the training data set. And that resonates very well what Richard Feynman famously said, what I can't create, I don't understand. So conversely, while a very ambitious goal may be, well, if we can create synthetic medical claims data, will it help us understand the underlying processes that give rise to that data? Can we get a better understanding of of health and healthcare? So now the first question, what is synthetic? So obviously, well, synthetic is an object made by a process that's different from the natural process. And then there are a couple of other key points here that products should have similar important features. Now, the question is what is similar in what sense and what is important? So if we look at synthetic diamonds, well, yeah, that they're made by an kind of synthetic process, but they have exact chemical and physical properties. So not very interesting from our point of view for that particular kind of project. Synthetic leather is getting closer, while the chemical composition is different, as expected. The look and feel is similar to real leather. Now, what is look and feel? How can one quantify it? And what is similar in what sense? And again, how can one quantify and use it for kind of to validate the synthetic object. A closer to our objective is a DALL-E project that's a GPT-3 team released somewhat, well, a few months back. Well, that model can generate images from text descriptions. And so it combines unrelated concepts in plausible ways. And again, the key point here is what is plausible? And that becomes very important for health data because the data should have synthetic health data should have similar statistics, but it also should be reasonable or plausible from the clinical point of view. So why do we need synthetic data in healthcare? Well, there's a lot of data in healthcare. It's one of the most data rich say fields. Now, one is that synthetic data has not always been realistic or has a similar scope. Now, there is a Mimic3 data set that's publicly available. I mean, you have to go through certification, but you can get access to that. And it powered a tremendous progress in the field. And yet, it's a de-identified data set from contains electronic health records from ICU for 40,000 patients. There are other data sets in the Mimic3 right now. And so if somebody is interested, well, that would be a great resource. And yet, again, it's limited. Then data sharing in healthcare can be a complex procedure because of strict privacy laws about personal health information, so PHI, and the difficulties of de-identifying data. And the challenge in de-identifying data is what's the trade-off between taking scraping off the information and masking and leaving enough so that the data remains usable. And the other 2 points is that healthcare data has historically has been accumulated, safeguarded by a few organizations so that healthcare providers, well, medical practices, offices, hospitals, and large medical systems, and health insurance organizations such as Anthem. And so the data for each person becomes fractionated over time. When somebody has insurance with one insurance company, while that person goes to the medical office, well, gets services, the claim is submitted to that current health insurance company. When the insurance changes, that data is submitted to another one. And so now over time, the record for each person gets accumulated in many different places. So current approaches to generate synthetic data. One is sampling from independent marginals. So the data contains, well, different elements, well, in particular, diagnosis codes and procedure codes, lab results, maybe prescription data. And so one can get statistics from a data set and then match the statistics. What's lacking there is interdependencies between the different elements. And obviously, well, each of them are not independent. So diagnosis and procedures, well, generally going to go together in some way. Now, I would like to bring up this MD Clone. That's an Israeli startup in this space. They've done a great job in creating synthetic clinical data set that do capture interdependencies. They created a COVID-19 synthetic data set that facilitated some research. They also have been working with the Veteran Administration to determine best treatment for behavioral issues, other health conditions. And I would next bring probably the major player in that field is Cynthia. They create a full historical health record for a synthetic patient in what is called FHIR, F-H-I-R. It's Fast Healthcare Interchange Resource format. That's the format that enables interoperability of clinical data between different data sources. And Cynthia the approach has been to create generic modules specifically for each of a couple of dozen conditions right now. And these models have been created in collaboration between clinicians and statisticians. So again, that's a very powerful and rich resource for synthetic data. Moreover, they open sourced it. So one can actually go to GitHub and then use the code to generate synthetic data sets of interest. So now our solution, and the difference is that we are looking at claims data. And again, why claims? Because claims constitute some of the largest health data repositories in the US healthcare system, because every time a person with insurance goes to a doctor's office, while a diagnosis is established or procedures are done, then the claim for that service is submitted to a health insurance company. Claims is a financial document, but it also contains diagnosis and procedures. And as such, claims contain a vast amount of health data. And we want to leverage that information to enable AI research and development, and, well, in general, work to improve healthcare. The technologies and platforms that we use. Again, this is just to emphasize that that's a large amount of data that required quite a bit of computing power. And so team has used multiple technologies, frameworks. We used AWS. So that's a brief, that's a list of the main technologies used. Well, there are quite a few other elements, but overall that's a very computer intensive project. So now we used a generative adversarial network model to generate synthetic data. That's been introduced by Ian Goodfellow a few years back. The image is from the MIT Technology Review, in which, well, they call it the Gunfather. Just, well, couldn't resist to use it. So let's imagine that we want to train a model to pass a version, like medical claim version of a Turing test. So that model will generate a claim data. So that's an example. Well, claim 1, line 2, E11621. That's a diagnosis code for diabetes. And then 99214, that's a what's called procedure code for an office visit. And then A3036, that's again a procedure code for HbA1c. That's a diabetes related blood test. So that kind of seems reasonable. So the question is, okay, whether that claim was generated from a real office visit or was it generated by a model? And so to train it, if you look on the left, the overall model structure is that there's a discriminator that tries to discriminate between the real claim on top or a synthetic claim at the bottom. And then the discriminator and generator are being trained until the discriminator cannot distinguish anymore between real and synthetic. And at that point, generator is trained, and then it can be used to generate synthetic claims. So some details on what we on the approach that we used. We used an autoencoder first, step 1. And there, well, we trained encoder and decoder, and in particular decoder. The trained decoder then was reused in step 2, in which it became part of the overall generator network. And so when the model is done, the input is a multidimensional random noise, and then that's in the end converted to a synthetic claim, and then the discriminator tries to identify whether it's real or synthetic. So now the key challenge here is how to evaluate differences and similarities between the synthetic and real data sets. So the challenge is, okay, well, each claim can be viewed as a point in a multidimensional space. So we had overall 657 dimensional space. Well, it's a sparsely, it's a sparse matrix where ones and zeros correspond. Ones correspond to a particular diagnosis code or procedure code that's present in a given claim. So one approach to quantify the similarities to use scale divergence between these two different distributions. We actually use Frechet distance to evaluate how close those points are to each other. That measure has been used in GAN literature successfully, and it worked really well for us. So what it does, well, you pick a point and then you figure out what's the closest distance by whatever the distance is defined. From that point to the points in the other distribution. And so the question, okay, well, how well does our synthetic data resemble real data? Now, we looked at patterns. And because in the end, patterns will capture interdependencies between the different elements, and patterns in the end will determine not the statistics, but the semantics of the synthetic data set. Does it generate clinically plausible claims? One surprise actually was that out of about 4 million claims, well, we found that half of them had unique patterns. And that may partially explain why it's so difficult to understand, first of all, the overall overall kind of typical patterns in somebody's health history, and also while it shows why it's hard to detect fraud, for example. Now, synthetic data, well, the same distribution. We got about 50% of claims contained unique patterns. And so when one look at patterns, what we did, we looked at short patterns, well, with 2 elements, say it would be a diagnosis code and a procedure code. It could be longer patterns, it could be 1 diagnosis and multiple procedures. And then we looked at patterns of 2, 3, 4, 5, 6, and more elements. And it turned out that, yes, well, there are a lot of patterns that are common, but then as the pattern length increases, and obviously, well, the shorter patterns are more common between the real and synthetic. But as the length of the pattern increases, then the similarity becomes less and less pronounced, which is good, because what it means is that, well, the longer patterns are probably less frequent, and they're also maybe more indicative or can be easier attributed to some, well, maybe not individual patients, but smaller group of patients. And so at this point, the fact that synthetic and real data diverges means that, well, there is a very low risk of violating privacy. And so business use cases for synthetic claims data. Again, well, there are multiple. I just list here a couple of them. One is population level research. And again, that the important part here is that if one has a model to generate synthetic data, then it all depends on the training data. So if there's a population of interest, then the real data for that population can be extracted, used as a training data, and then that train generator then can be used to generate data that will be similar in many important ways to the underlying training data or to the data for that population of interest. And the synthetic data then can be used for analysis and research without violating privacy. Exploratory analysis, again, because of the very strict privacy laws, it's not possible for somebody just, well, let me look at the data and then figure out then what my question might be. Usually it's required to state the purpose and maybe sometimes even a hypothesis before you can actually access the data. And so synthetic data enables some, and it would enable people to do exploratory analysis, to come up with the questions and hypotheses, and then determine the approach, and then maybe, if needed, request to use real data. Cost analysis and predictions, and well, they use this Higgs-Pix or CPT codes, code distribution. These are procedure codes. And again, because claims are essentially financial documents with health information, they contain cost for each procedure. And that means if somebody wants to understand the cost, well, that would be an ideal way, ideal data source, because it contains both health information and cost information. And then internal operations for a health insurance company, that will be testing of claim processing, claim validation systems, in which one can generate synthetic data in the exact format that's required to test various systems. But again, it will not, the testing will not involve real data. And so that means that it's much safer process without the risk of violating privacy. And then testing and validation of AI ML models. Well, one of the ways to validate or evaluate the quality of synthetic data is, let's say, well, one can train a classification or regression model, let's say on real data, test it on real data, and then test again on synthetic data and see how it performs. Conversely, and more interesting application is one would train a model on synthetic data while you train, validate, test on synthetic data, but then test it on real data. And if the model performance is similar between the real and synthetic data, that suggests that that model can be actually usable later on. So that's a brief overview of the synthetic claim data work that our team has been doing for some time. We're writing it up, so more details hopefully will be available soon.
Mark, we have one question.
Yes.
George asked the question, how can a healthcare provider evaluate these different synthetic data engines, such as MD Clone and Cynthia? So
with Cynthia, actually, we generated synthetic patient data from Cynthia and then did analysis on statistics and their dependencies, and we compared it with our data. So again, the format from Cynthia data is different, and also Cynthia creates full historical health records versus individual claims that we do. But the statistics can be evaluated, and that's what we did. With MD Clone, then we would need to work with that company if there is interest, and then evaluate.
Great.
All right. Shall we talk about ethics and AI? Thank you very much for tuning in, and thanks, Mark, for presenting your work on synthetic data. So my name is Sasha Gutfraind. I'm a principal data scientist at Anthem. I work closely with Mark. And today my goal is to give you a fresh look at AI ethics in healthcare. I will build upon some of the previous talks that you heard in this seminar series, but I would like to also highlight some issues which were not raised in the past, and also give you some tools which will equip data scientists and people who are doing this software in your team. Can we see the next slide? Right off the bat, I would like to highlight that ethics, in my view, is an extremely subjective field. There is no right answer in ethics. There is perhaps a wrong answer in ethics based on bitter experience that we had. But ultimately, every one of us who is required to make ethical decision when we are building a solution, when we are evaluating solution, we find ourselves in unique circumstances that might have not occurred before. And so we need to look at the different ethical criteria, look at the resources that are available, and make the best decision we have. So I think what you're going to hear is my opinion on some of these topics. Your opinion might be different, but I hope that we can agree on what are the criteria are and what are the defining ethical concerns. This is certainly a field that's evolving very rapidly. So much has been said in the past 2 years, and I'm sure that the next 2 years will involve a lot more research and study of this area. Let's look at the next slide. So the structure of my talk is basically going to have 2 parts and Q&A at the end. In the first part, I would like to kind of deepen the questions and talk about some of the challenges that we have when we are building AI solutions. And then the next part, I'll talk about some of the tools that are available. And you would be surprised how much technology now has been built in order to make ethics easable and feasible. in AI. So let's look at the challenges. The first and perhaps most familiar story that you've seen is the study of the Impact Pro algorithm by Obermeyer et al. That appeared in Science now 2 years ago. Essentially, in this algorithm, you've seen this before, there was an algorithm that tried to identify which patients of a hospital will require additional interventions. And this algorithm did not use race as a variable. That's very important. However, it was ultimately designed to prioritize patients based on expected healthcare cost. Cost is very readily available. Unfortunately, Black patients had lower cost when adjusting for their state of health. And as a result, when this algorithm was applied, what we got was an underrepresentation of Black patients in the group getting that intervention. So they were basically getting less healthcare services. So what do we learn from this algorithm? And what are the challenges that we really need to solve as data scientists that building these solutions, or maybe not just data scientists, but engineers and also administrators? First of all, it is very easy to make an ethical transgression, to actually cause ethical harm. The techniques that these data scientists have used are standard techniques. They are very commonly used in the literature, and they're used almost in any organization. Secondly, they were not probably trying to be bad. They were trying to do cutting edge data science, and they were even deliberately trying to avoid giving race a consideration in this planning algorithm. And nevertheless, they got into a lot of trouble for the algorithm. And I think third conclusion we have to highlight is the data is very challenging. We cannot assume that the data that we have access to is free from problems. In fact, there are some problems that are sitting under the surface that we need to be aware of. So let me talk a little bit to you about some of the data challenges. This is an example of the kind of disparities and challenges that we have in healthcare data. This is a data from the journal Cancer from 2014, comparing cancer mortality rate across different populations, across different race groups in the US. You can see prostate cancer, breast cancer, and colorectal cancer. If you just look at, say, the blue lines, the blue bars, you will see that for a variety of reasons, African Americans have double the mortality rate for cancer of whites. For Hispanics, it's a little higher than whites, and Asian Americans seems a little lower than whites. That is the data. Why are these disparities present? There are many sources for these disparities: social, economic, biological, perhaps, different medical practices, geography, technical practices. So if we are using data, for example, building an algorithm that assists in medical decision-making or population health planning for cancer, we have to be aware that our data might represent disparities. And sometimes we don't know what is the source of these disparities. We have to be, of course, very careful about building AI using data that contains disparities. Let's take a look at next slide. So I try to summarize here some of the challenges that are often missed when we think about data science and AI in healthcare. And I think that the challenges go beyond simply data. I divided the challenges toward challenges faced by data scientists versus challenges faced by managers and users. Let me talk about a couple of them. A basic problem in data science is that we frequently don't have the resources or we face constraints. We sometimes are limited to using one data set. We sometimes have a time limit as to how long the algorithm develop could could take. We frequently have trouble identifying the causal effect of some of the outcomes that we are seeing. And that's problematic because if we are building an intervention, we don't have a good handle on the causal process that brings out these outcomes. Speaks a little bit about the point that Mark made about generating the data. We cannot generate the outcomes in the lab. So we have to be very careful about the causality and the interventions. And something that is very not frequently mentioned, but very important in my mind, is the fact that a lot of the algorithms we build need to be really monitored after they deploy them to make sure that they're used in the wild by users in a way that's appropriate. On the other hand, managers and users have similar constraints in terms of lack of resources. Sometimes they're forced to maximize sales, and as a result are challenged to omit some of the limitations and ignore some of the problems with the algorithms in order to maximize sales. Sometimes users don't have sufficient training to use the algorithms or misapply them to uses that are not intended. So there is a lot of problems, a lot of challenges building good AI for healthcare. So let me talk to you a little bit about the tools and solution. I would like to start from the most broadest structuring this in the kind of broadest way possible by looking at biomedical ethics in general. Next slide, please. Yeah. So what are the sources of biomedical ethics? So if you wanted to build something that's maximally ethical, where do you need to look? Which books do you need to open? So a lot of the times when we work as data scientists, we actually think about what numbers 3 and 4 in this list. So we try to build a solution that is efficient, that gives the most healthcare to the most people. We have a population in the medical center or population in a large system. And we want to give a solution that will, say, monitor these patients and give it the best health to most people, while number 4, respecting their privacy. And so that's where HIPAA comes in and tells us what we can and cannot do with data. But this is a somewhat utilitarian perspective on algorithm development on AI. If you speak to a doctor, the way doctors think about medicine is somewhat different. They think of it in a more deontological way, which is as a kind of a duty of a provider, of a doctor or a nurse toward their patient. And that duty sometimes conflicts with the utilitarian system design. See, every patient is unique. Every patient has a unique medical history, a unique story, a unique set of constraints and challenges. And so if you build a system that serves the most number of people, you might not actually build a system that serves that particular person maximally. Doctors actually try to do that. And so some of the things that are big concerns of medical practitioners, doctors, is so-called Declaration of Geneva, which is the modern incarnation of the Hippocratic Oath, the duty of individual doctor to their patient. And it talks about things like justice, about autonomy of patients, giving them the ability to make decisions on their own, practicing medicine without regard to the costs of procedures. Second consideration that has become is very much important to us is the issue of the Belmont Report. The Belmont Report came in the US to define what is allowed to do when we do scientific research. And arguably, when we are developing algorithms, we are using data in order to do research and development. Sometimes we are not able to get individual consent from the people who were including that in that data set. So that's another consideration that's very important. And these are considerations that that all need to be looked at when you're talking about ethical AI, in my view. Let's look at the next slide, please. Let me give you an overview here about what could be called vulnerable population. So I talked about race, and the racial minorities are certainly considered vulnerable population. But when we are thinking about AI, that is not the full story. According to this paper by John Francesco, there is actually a much broader number of populations that are vulnerable. That includes generally groups with low socioeconomic status, SES, but racial minorities, immigrants, individuals with behavioral issues, and I would probably also include children, the elderly. A lot of these people have certain unique challenges when facing the healthcare system. For example, immigrants, I think a poorly understood point is, for example, that vaccine, if you look at COVID vaccines and different populations, immigrants have some of the lowest uptake of COVID vaccines. And part of the reason is because they simply don't have poor access to English. As a result of that, they don't understand the information that's available about COVID vaccines, and in fact, they frequently receive misinformation, and so forth. So there's a broader spectrum of groups that you have to be worried about, I think, when you think about vulnerable populations. In general, vulnerable populations are somewhat different than the majority. Here's some of the differences. They are frequently treated in different medical settings, frequently use more acute care rather than ongoing disease management. Care is more fragmented, going from provider to provider, resulting in more gaps in data. And generally have lower access to and use of electronic systems. This is particularly important for example, the elderly. And as a result, we get smaller sample sizes, poor quality of data, and generally poor performance of algorithms. So this is my point about vulnerable populations. Let's look next. Let me tell you a little bit about sensitive variables. So one of the basic questions that we have is when to use a variable like race, or even harder question, a variable like gender and age. This is where the subjective judgment comes in a big way. There are situations where variables are appropriate to use in the healthcare algorithm. These sensitive variables are appropriate, and there are situations where they are not appropriate. There are many medical algorithms that include age as one of the predictive factors, or as gender and even sometimes race. Certainly, most medical algorithms consider the healthcare history in order to establish some kind of a diagnosis or care procedure. But all of these could potentially be problematic. For example, if your algorithm is making a financial decision that may harm a patient, then ethics might demand that you not include these categories, some of these or all of these variables in the decision making. Certainly, generally, what I find is that there is justification for using these variables if they can help the algorithm provide the most appropriate care or correct for biases that are present elsewhere. What we frequently can do is to design the algorithm in such a way that the bias, potential bias that might be present in the data or might be present in the variables that you're using is mitigated in some ways. And so this is a topic to itself. A common practice that you see in healthcare data is so-called demographic blinding, which is to remove very sensitive variables, particularly race. This is not an entirely. This demographic blinding does not get you out of trouble entirely, because as you saw with the impact pro algorithm above, the algorithm might still have bias through other means because of data issues. Race might be correlated with the zip code, resulting in bias, inappropriate biases. So a lot to think about here. Let's look at the next slide then. So I alluded to that there are strategies for mitigating bias and outcomes. So let me review some of these strategies. And so there's a whole literature about bias mitigation strategies in the most common use case of supervised learning. This is when we are, for example, trying to predict 0 and 1, whether a person will have, say, a readmission to a hospital or not. There are many strategies, and this requires a lot of data science skill to implement. And I'll also talk to you about the slide on the right a little bit later. So some of the strategies that we have is to use a target variable that is known to have low bias. So in the Impact Pro example, they used a target variable, which is cost, which is known to have a lot of bias, because cost depends on whether a person has access to health, which providers they use. So a variable that they could have used instead would be, for example, a variable that depends on an unbiased characterization. One idea that I've seen proposed and tested was to look at acute admissions to hospital. So rather than predicting cost using all these variables, build an algorithm whose target variable is the expected number of acute admissions. There are many ways of designing an algorithm for supervised learning. And so frequently when we see an algorithm that results in a lot of bias, we can redesign the algorithm in various ways to reduce the bias. For example, we could select different variables, change the data set. There are actually toolkits, and this is where you see an illustration here. There are toolkits that allow you to select a low bias algorithm. I think this comes from a toolkit from Microsoft called FairLearn. Over here in this scatter plot, you see the modern precision for different models, and that's on the horizontal axis. On the vertical axis, you see the true positive rate disparity. So this is something that you want to reduce. You want to have lower disparity in the true positive area. So the algorithm has about the same disparity across different categories of people. So you can see that the optimal algorithm has a model precision of about 0.55 and TPR disparity of just about above 3. But this toolkit allows you to select an algorithm that has a lot less disparity with almost the same model precision. And you can see some points on the far right, which are almost as good as the algorithm that is optimal. The last strategy for bias mitigation, and it's not necessarily the most recommended, is to apply post hoc adjustments to improve fairness. But the problem of that is that you block a snake in one place and it can pop its head in another place. So this is not necessarily the most recommended strategy, and that involves adjusting the outcomes, adjusting the predictions in some way in order to rebalance them. Let's look at the next slide, please. So if you're considering building an algorithm right now, there is actually great toolkits that are available to evaluate how good the algorithm is doing. You don't have to write code yourself. The code is actually readily available through existing toolkits. So the toolkit I really recommend is something called Equitas, and it's a tool developed at the University of Chicago that allows pretty much quickly evaluate your algorithm in terms of any potential biases and different types of errors. Now, that said, this is not a panacea. There are so-called fairness trade-offs, namely mathematical impossibilities. For a given classifier, there is a trade-off between error rates in different subpopulations and so-called calibration essentially how good the algorithm is within each population. Now, as a result, the current advice is to select what is known as the fairness metric. In other words, to figure out which metric is going to be the primary metric, which is going to be your primary ethical concern. And to show how this works, they provide a tool called the equity tree. Let's turn to the next slide and take a look at that. Sorry, it's called the fairness tree. The tree starts from your algorithm, and it gives you at the bottom a certain a metric that you should be most paying attention to. So let's navigate through this tree just to see how it works. So the first decision that you have to make is to tell us if the algorithm is going to be a punitive algorithm or assistive algorithms. So punitive algorithms are some of the algorithms that are used, for example, in parole decisions to deny parole or to deny bail, decisions typically involving policing. That's on the left. On the right, these are the typical healthcare algorithms, which are assistive algorithms. So we are going to follow that branch. Assistive algorithms basically provide additional benefit to certain members of the population. So next decision is the intervention with most people or only a small fraction that need that intervention. So in the small fraction is cases where you have a very expensive intervention program that is going to be benefiting a small number of people. So so maybe it's like, say, an intervention that costs tens of $20,000, hundreds of thousands of dollars, which will prevent an important but severe health outcome. So in that case, so that would be the left option, small fraction of people. Then the metric that you're most concerned with is recall parity. Recall parity means that you're selecting from each subpopulation, so from category, a proportion number of people. So you don't want to be in a situation where you're missing all the immigrants simply because they forgot to fill out a form of some sort or have trouble filling out a form. So that's recall parity. You're going to get about the same parity from each population, same amount of people from each population. However, a lot of interventions are different. The interventions are focused on the large segment of people, for example, giving them an inexpensive medical app or providing them with some counseling. In this case, the picture gets a little bit more complicated. And so there's other metrics that you need to focus on. But that's how the fairness tree works. I think it's a great tool, and I think this is something that we should all consider when building an algorithm for healthcare. Quickly, let me also highlight a couple of new developments in the field. A lot of organizations came out with guidelines and standards for developing efficient and successful algorithms. The IEEE have standards for algorithmic bias. Anthem, for example, has its own in-house standards and AI governance system. I really like this paper by Joe Bin about the global landscape of AI ethics guidelines. So it has kind of like an overview of this rapidly whirling field. We have Bo Norjo from Anthem actually developed a disclosure process for reporting on the performance of algorithms that goes through these analysis. So I think that's something to look at. And I think the slides are available to you after my presentation. Let's look at the next slide, please. So to summarize, I think that all of us have a role to play. And I think it's not really just on the data scientists to build the perfect algorithm. I think that, in my view, the sponsors, stakeholders need to make sure that they invest the right resources in developing high quality algorithms that the resources are available to address possible biases. But they also need to understand that how to use the algorithm. It is not, AI is a technology. It is not okay to just plug and play numbers and assume that everything will just work smoothly. data scientists I talked a lot about. Not only we need to understand the problem, we need to understand the data, we understand the intended use and the limitation of the technology, and then at the end validate that the actual use is ethical and appropriate, and it's as designed. And I think the users ultimately also have a responsibility to understand how AI works and make sure that it's used in a holistic manner for intended purpose, and frequently relying on additional context and data. So it's a complicated story, and I'd love to stay in touch with you if you have any questions about what I spoke. Thank you.
Well, thank you so much, Sasha. I saw that we have one question. It's actually more on the synthetic data side of things. So for Mark, I guess, asking whether or not synthetic data engines can be used for NLP. Mark, do you want to take that?
Yes, thank you, Dan. As of now, it cannot. At least our version cannot, and the versions that I've seen so far cannot, because the synthetic data, well, that's a series of codes, and that's not really NLP part. Although I must say that, well, one can think about this kind of series of claims and health records as a story. So it's quite possible to use NLP techniques, NLP models, but the substance itself is not. The data itself is not NLP.
Okay. Another question, this one is actually for Sasha, asking whether organizations such as the FDA are looking at ethics when they evaluate algorithms.
It's a good question, and I will have to look at and to see what the answer is. But I wouldn't be surprised. I know that another government agency, NIST, I think released information about ethics of AI. So I think that it's I'm not sure if FDA would be like specifically looking for this. But I wouldn't be surprised if they do it. It's certainly a lot of government agencies are involved, and there's a very rapidly growing body of literature in legal literature around AI ethics, a body of law that's emerging, and I believe that there's a couple of there's certainly a lot of proposals. At Congress, and there's a lot of regulatory requirements now on some of the makers of AI for compliance with ethics. So I don't know the specific answer about the FDA, but I think overall a lot of regulatory activity.
I have a question that I was thinking about as you guys were both talking is whether or not the use of synthetic data can help with sort of the, when you have a lack of healthcare access in certain populations, could you generate synthetic data just to kind of control for some of those factors, and whether or not that's something you guys have considered?
Well, we haven't done anything yet. But that would be one of the potential applications. And kind of maybe a general statement that if you think that intelligence in the end, well, provides pattern recognition and reasoning to enable decision making. Now, artificial intelligence for now is good with extracting patterns, but not reasoning and not decision making. And so the idea that, well, we can use AI to extract patterns and then analyze them and then take corrective measures as needed, that's an appealing prospect. And that would be one of the, applications.
Thanks for telling me for not telling me that I'm crazy.
I don't know if, can you hear me okay? I can't
Yes.
tell. Yeah. So first of all, I applaud Anthem for taking such a leading role in thinking about both bias, but also pushing the envelope on synthetic data. I was wondering, like, from the synthetic data standpoint with Anthem as a payer, like, what are some of the, are there specific applications that you are really focused on with the synthetic data that you're able to generate now? Or is it that it's still sort of just pilots and experiments, or is there a specific application you're really pushing for now?
I think I would not go beyond the list of kind of potential business uses that were on that slide. And again, because while we are, I wouldn't say the very beginning, but that's kind of early stages.
Yeah.
With the claims data, and ideally, I would really like to see a combination of claims data and augmented with clinical data.
Yeah.
And so now you have a synthetic data set overall, and you can use it for multiple, multiple applications.
It's interesting too, because, and I also, Sasha, I wondered, you mentioned this issue of bias, of data bias, and is there some intersection between these worlds of synthetic data and bias? Can you use synthetic data to fill in gaps, to create sort of like, because right now we have this sort of quilt work of these different data elements, and obviously we have poor capture on certain demographics, as you pointed out. But where you do have deep wells, is there, and I've seen this done, for example, in certain epidemiological studies where people will use interpolated data to sort of fill in sort of the trajectory of a person's of life, of what we think would be captured for a person, let's say in a cohort study. So I wonder, is there some role here for synthetic data in addressing some of these bias issues?
I think absolutely, and I think it's a great suggestion. Great suggestion. It's I think for a lot of patients we get like a slice of their medical history. So for example, if they join Anthem in the past 12 months, we will just not have their medical history. The previous 12, their entire life we would not know. So can we synthesize their data based on just knowing the last 12 months? That could be quite valuable type of idea. So I think it's great. I think it highlights your question, like brings up some of another possible way of using synthetic data.
Yeah. I'd probably like to add to that that may be one of the very good uses for synthetic data, because it actually, when done well, it does capture all these biases, and then it allows lots of people who would not have access to the data otherwise to actually do that exploration and analyze what's there, what biases are there, and then relate it maybe to other available data sources. And maybe one brief comment I would like, while we have a minute, I would highly recommend the book, The Ethical Algorithm by Michael Kearns and Aaron Roth. It's a fantastic book, and it goes into this Pareto frontier for fairness versus accuracy trade-off, differential privacy. Just fantastic book.
Yeah, it is funny, isn't it? Because the world is all about distributions. so I think synthetic data is really about the distribution of data. So, pandemics are about distributions. I mean, everything's about a distribution. So I think it's interesting to see. That's a great book. You're right. So
yeah. So as you can tell, we could probably talk amongst us all day long about this, but I do want to be aware of time. We're at the top of the hour. I want to thank you, Sasha and Mark, for sharing your knowledge with us. I think you guys are doing bleeding edge work, and I think the students have learned a lot from the work that you're doing. Thank you so much.
Thank you, guys. Thank you.
Thank you. Thank you for inviting us.
Thank you.